Okay, so what we're going to do is be able to calculate the change in enthalpy for a particular reaction by using our standard enthalpies of formation, and that's why these are so useful. So we're looking at the reaction. Now, this is you got to go back and compare this to bond energies. Okay, we talked about bond energy. We said the reactants are going to be endothermic because we have to break these bonds, right? Because we have to break this apart so that we can then create our product. So therefore, we're going to release energy as we form the bonds on the product side. Now, keep in mind the definition here. This is the standard enthalpy of formation. So this is going to seem backwards to you at first, right? Because this is energy of formation. So what I'm going to do is, am I forming these? No, I am not forming these. I am actually breaking these down. What I'm going to do is form these on this side. So our energy values that are in this chart, if you think about this chart here, these are the energies of formation. Okay, so if I'm forming this, then the energy is released. If I am breaking it down, then I have to make it positive. It's kind of the opposite of what we did with the bond energy chart. The bond energy chart was almost always positive. A lot of these are all going to be negative. So keep that in mind as you're looking at this. Now, if you use this equation down here at the bottom, what this equation is going to do is by putting products minus reactants, it's going to change the sign notation for you. Because if you're subtracting the reactants, your reactants are the ones that you want to change the sign notation for. Okay, with bond energies, we change the sign notation of the products. Here we're changing the bond energies of the reactants because we're not forming these, we're breaking them apart. Okay, I'll show you an example, so just kind of bear with me here. Okay, so what we're going to do is we're going to sum up this side just like we did for the bond energies. We're going to sum up this side and then we're going to compare the two. But this equation kind of does it for you, and I like this equation, so I would recommend you try using this. What this means is a summation, so you're going to sum up all of your reactants or all of your products. The M stands for the coefficient, so that would be your coefficient, so you have to take into consideration the coefficient that you have. And then this is your change in enthalpy of formation. And the little degree symbol, I don't know if I mentioned that earlier, signifies standard state. Okay, so what that means is that we can use this chart because this chart is under standard states as well. Okay, all right. So what we're going to do is sum all of those up, and then we're going to take the summation of the products and subtract it from the summation of the reactants, taking into consideration the coefficients. Okay. Okay, so we're going to use standard enthalpies of formation to calculate the change in enthalpy for this reaction. I changed this from reaction to combustion just because I know that it's a combustion reaction, and you don't necessarily have to do that, but it just kind of helps to recognize this as a combustion reaction. Alright, so I wrote down the equation. I got the summation of the products and the summation of the reactants. So I'm going to rewrite this in terms of the substances. Okay, so what I did was I replaced the reaction. I've got the M is my coefficient. So I put that down here for each of these. And then I just replaced products with the actual products themselves. So now I'm going to do is I'm going to use my chart over here and I'm going to plug in the numbers. Okay, so I'm going to plug the numbers into the equation. Alright, so let's do that. Okay, so I replaced this information here. Let me do a different color. I replaced this information here from the chart. Okay, I replaced this over here. Now notice that this one here I put as a 0 because anything in its elemental state, like oxygen or hydrogen, is going to have a value of 0 if you look it up on the chart. Now one thing to watch are the sign notations, negative, negative, negative. You don't have to remember to change them like we did with the bond energies. Just take them from the chart as they are, plug them into the equation, and you should have no problems because this is going to self-correct the sign notation. Okay, it's going to self-correct it for you. I'm going to finish simplifying all of this, and we'll take a look at the answer. I simplified everything and brought all my units together and finally got my answer, which is negative 1,357 kilojoules. That would be the change in enthalpy for the combustion of this reaction. So for every 1 mole of the ethanol that reacts, this is the amount of thermal energy that comes out of the combustion reaction, and that's the number that goes here. Alright, a couple things to look at is keep in mind if they might give you this number. One typical thing that they do is they'll say that the heat of combustion is, because you can get this from calorimetry. Remember, we can put this in a calorimeter and experimentally find that heat of combustion. Then they might say, well, what is the change, or what is the formation energy of the ethanol? Well, you can look up this number and you would be solving for this. It's a very, very typical problem that you could see in the AP test where they don't actually have you solve for the combustions because we can actually get those from experiment. The formation energies are sometimes hard to determine if it's a new substance. So, all right, so that's really important to focus on because we're going to use this for all types of state functions. So in free energy and entropy, this strategy is used quite often. So I hope that helps you get started, and I will see you guys in class.